Yeah, good morning. It's about 9 o'clock, at least in my clock. I see people are trickling in, so I think we give us 1 or 2 minutes before we really start. All right, let's begin. So I welcome you to the 2020 SIAM CAMES Joint Annual Conference and also the SIAM Conference on Image Sciences. These are organized together. And if you look in the program, you see this AN20 for the annual joint meeting and the IS20 for the Image Sciences Conference. My name is Thomas Hillen from the University of Alberta, and I'm the current president of CAMES. These are exciting times for applied mathematics. The world is moving fast with technological development, telecommunication, transportation, climate change, and of course, epidemic modeling. The coronavirus pandemic has brought applied mathematics into the daily discussion. As applied mathematicians, we understand the use of models, we understand what R0 is, and we understand the meaning of flattening the curve. Some of us actively participate in the modeling of COVID-19 and advise governmental strategies. It is easy for us to get involved in this discussion, and it is understandable that we get frustrated if governments ignore our advice. The boost through the coronavirus modeling for our discipline brings opportunities and challenges, and we are asked, no matter what we do, to always apply the highest standards of scientific exploration. Of course, the coronavirus pandemic has significantly disrupted our plans for this meeting. Registration of sessions happened with the understanding that we all meet in person in Toronto. But now, of course, we had to move everything online. And not all session organizers, not all plenary speakers were happy with this choice. But I'm glad to see that so many of us agreed to participate and to do their best to make it work. We have a full 2-week program with plenaries, prize lectures, industrial panels, student events, poster sessions, and mini symposia. It is important for me to note that we adhere to principles of equity, diversity, and inclusion. Everybody is welcome in our meeting, and we do not accept discrimination based on race, gender, sex, religion, age, or ethnicity. Our conference is a safe place where each contribution is treated with respect and each voice is valuable contribution to the meeting. The organization of this big online meeting is not a small enterprise, and I'm grateful for the help of the organization committee and my co-host Leah Bronsard from McMaster University. Unfortunately, Leah chose to not participate in the online version of the meeting. I'm extremely grateful to the work of the SIAM team, in particular Richard Umur and Connie Young from SIAM. The online meeting is run on this virtual event place platform. The program with links to all the sessions is available. Posters are available under the halls, alphabetized by the poster title. And I really recommend that you go and browse through the posters. They will be up for the entire 2 weeks. Attendees will also find a complete list of all sessions and all posters on the SIAM websites, if this is easier to navigate. Speaking sessions have a seat limit of 1,000 participants. We will monitor attendance and increase capacity if really necessary. But please also keep in mind that the talks will be recorded and they are available on demand on this platform. The block lecture, which is happening right now, and the John van Neumann Prize lecture on Friday will also be publicly streamed on the SIAM website. A few events listed in the program will not be happening on the platform, but outside. For example, the CAMES AGM and other meetings. And so please be conscious about emails you might get about various Zoom logins. All times are listed in Eastern Daylight Time, so Toronto time, and session time limits should be enforced so that we can have parallel sessions and people are allowed to switch between sessions. Make sure to check the exhibit hall with booths from SIAM and from our sponsors and other societies. And also the network lounge is a good place to chat in groups or one-on-one. And remember, although well organized, there will be glitches. There will be unstable Zoom connections, disrupting background noises, speakers misreading the time zones, etc. So please be patient and try to help each other. And then I'm sure it will all work out really fine. SIAM and the Conference Organization Committee wish to extend their thanks to the US National Science Foundation for its support for the workshop celebrating diversity and of the professional development programming being offered as part of the annual meeting. Finally, at the end of the conference, all participants will be emailed a survey. We are all participating in a grand experiment with the virtual conference, and your feedback is more critical than ever in guiding how we organize such meetings in the future. Please be sure to fill it out at the end. Now, I wish you all a very good meeting. And let me now introduce Lisa Fauci, the president of SIAM.
Hi, Tom. Thank you very much. I think Rebecca Tyson has joined us. Does she want to say a few words?
Oh, that would be fantastic, Rebecca, please.
Yes, hello. Sorry, I was a few moments late. Je voulais vous inviter à rejoindre cette conférence en français. Chers collègues, bienvenue à la conférence annuelle de la SCMAI de 2020, tenue conjointement avec SIAM. Je m'appelle Rebecca Tyson et je suis la présidente élue de la SCMAI. Cette conférence annuelle est un point culminant pour la SCMAI et nous nous réjouissons de pouvoir l'offrir sous forme virtuelle. Merci.
Thank you, Rebecca. So I am Lisa Fauci. I am the current president of SIAM, coming to you from my home in New Orleans, Louisiana. And this was not at all the 2020 annual meeting that I expected, but nevertheless, I am very excited that I am coming to broadcast to all of planet Earth right now. And so my duty here this morning is to introduce the Block lecture and award winner. And the Block Community Award lecture was named in honor of Ed Block, who was a founder of SIAM. And he was always greatly interested in the applications of mathematics, the exposition of mathematics, and its many uses. Today, we are pleased and honored to have Erik Demaine from the Computer Science Department at the Massachusetts Institute of Technology to be our Block lecturer and to win this award. Erik's interests range throughout algorithms, from data structures for improving web searches, to the geometry of understanding how proteins fold, to the computational difficulty of playing games. In 2003, he received a MacArthur Fellowship as a computational geometer tackling and solving difficult problems related to folding and bending, moving readily between the theoretical and the playful, with a keen eye to revealing the former in the latter. Erik co-wrote a book about the theory of folding together with Joseph O'Rourke. That's called The Geometric Folding Algorithms in 2007. And a book about the computational complexity of games together with Robert Hearn called Games, Puzzles, and Computation in 2009. Together with his father, Martin, His interests span the connections between mathematics and art, including curved origami sculptures in the permanent collections of MoMA, the Museum of Modern Art in New York, and the Renwick Gallery in the Smithsonian. So I know we are a few minutes early, so nevertheless, I am going to introduce Erik, and maybe you could just say a little bit more on your title slide for the people who will join at exactly 15 minutes after the hour. Thanks, Erik.
Thank you. It's an honor to be here. So you want me to just tell jokes for 5 minutes? Is that?
Well, you could begin. It's fine.
Okay, sounds good. Yeah, I'm here to talk about computational origami and mathematical origami, which is a really fun area of research and maybe a nice break from the complexities of real life that we're dealing with these last few months. And I'm Erik Demaine, as you heard, at MIT. And for me, mathematical origami is a way to combine together science and mathematics and sort of, provable study and, real problems we can sink our teeth into with art and sculpture. I come from a math and computer science background in Canada, Dalhousie and Halifax and Waterloo. And my father, Martin Demaine, who's mentioned, comes from an art background, glass blowing and so on. And we've known each other a long time. He's watching this video now. And we've sort of met in the middle and taught each other a lot, originally through homeschool. He taught me things like mathematics. Now I teach him mathematics and he teaches me art. And we make sculptures like the example on the left here. And we also work on the mathematical side. So it's a lot of fun working together. And I want to show you what fun things we do. So let's get into it. Origami is very old. Don't know exactly how old, at least a couple hundred years old, maybe a couple thousand years old. This is an early book on origami, sort of the state of technology in 1797, where we take a 1x3 rectangle with a couple of slits cut into it, and each of these squares folds into a classic origami crane. And if you keep these corners connected, you can actually fold many cranes out of one sheet of material, but it uses cutting. So that was high origami technology a couple hundred years ago. In the last few decades, that technology has exploded. So now out of a single uncut square of paper, you can fold a three-headed Cerberus or a dragon with 1,000 scales, which I'm told took about a year to fold. And now without any cutting, we get even more complexity than was possible a couple hundred years ago. How is this possible? Through our mathematical understanding of how we fold paper. These are some more examples. On the right, we have Brian Chan, who's an MIT alum, folding, for example, the MIT Mens at Manus seal, all out of one square of paper. This is one square of paper. Pretty crazy stuff. This is a piece of paper. It's black on one side, white on the other, and you can get color changes between them. And so Jason Koo, for example, is my PhD student and MIT alum. And when he was a high school student, he designed this butterfly, and he didn't just sit down and start trying to fold a piece of paper into a butterfly. He designed a pattern on a computer, essentially applying mathematical algorithms for how to reserve different parts of the paper for different parts of the model. And that's done through a theory called tree theory, or the tree method of origami design. That's co-developed by many Japanese artists and Robert Lang in the US. And we've been working together proving that this always works. So what this method does, stated as an algorithm, is you give it a stick figure. So for the mathematicians, this is a metric tree. It has its tree shape. And each of these edges has a length on it. Here, they're all the same. And the goal is to fold a kind of stick figure model. Say you wanted to make a lizard. You plug this into this algorithm, which is available as free software by Robert Lang called Tree Maker. It gives you a way to fold a square piece of paper into a model that has one flap of material for every edge over here. And they're connected in the right way. And so then you could imagine shaping that into a lizard. Here's a more complicated example. Sorry, a little bit too much ink here, where we want to fold a scorpion. So we draw a kind of stick figure of a scorpion with the right number of legs in roughly the right places, the pinchers. And the algorithm gives you this crease pattern, which you fold from a square, which turns into this base. And it's hard to see because there's lots of little flaps of material all on top of each other, but it has the same structure as this tree. And then with a little bit of shaping, you can fold it into a scorpion. So this part is sort of the art part. And origami artists are very good at that. But as a mathematician, this is a little unsatisfying, because on the one hand, we can fold any tree, which is pretty cool. But on the other hand, we don't have an algorithm that's going all the way to the final form. So most origami design is done using this tree method, but we've been looking at sort of the more general question. Suppose you have a square of paper. What shapes can you fold? Can I fold any polygon like this horse? If I have a piece of paper that's white on one side, black on the other, can I fold any zebra or any two-color pattern? And of course, we live in a three-dimensional world. What I'd really like is to fold that piece of paper into an arbitrary polyhedron. And we proved way back in 1999, this is when I was starting out as a grad student, that this is always possible. If you give me a very large square of paper, I can fold any 3D shape with any two-color pattern you want. But the method we gave for doing it is impractical. You take a piece of paper the size of the moon and you fold a microscopic zebra. But recently, in the last several years, we've been developing with Tomohiro Tachi this origamizer method, which is a practical way to fold any 3D surface. So you start with an arbitrary 3D model you design on your computer. You plug it into this algorithm. It's also available as free software called Origamizer. It gives you a crease pattern here. I've drawn the square, but I didn't draw all the creases in this blank region. And each of these little purple triangles is folding into one of the triangles on the final surface. And so you just fold that crease pattern and you get exactly the classic Stanford bunny model. And in this example, we use 22% of the surface area of the piece of paper. So about a quarter of the material is actually getting onto the final surface. The rest is being tucked into these little holes, which for origami is pretty good. You expect, most models use about a quarter of the material. So we can't prove that this method is always so good as a quarter. It's probably not always possible in general, but for real world surfaces, it seems to work really well. And we can prove that it always folds into the desired surface. Here's an example of actual folding process. Here we've, instead of folding from paper, Tomohiro is, this is an old visit to MIT. In fact, it was on the July 4th weekend that we folded this 9 years ago. And instead of a piece of paper here, we've laser cut a sheet of steel, thin sheet of steel. We cut out some holes because steel is a lot thicker than paper. And he's folding by hand that sheet into steel bunny. Took about 10 hours to fold, similar to a paper model, but this is a lower resolution bunny. And so the idea is, out of any sheet of material that can hold a crease, you can fold any 3D surface you want. And this starts to get exciting, not just from an art perspective, but from a practical manufacturing perspective, engineering and so on. Sheet materials is a great way to, is a great starting point for building things. It's cheap, it's easy to ship, has great economy of scale. And so you can imagine, instead of shipping, when you order the next thing you order on Amazon, say, instead of it coming in a big three-dimensional box because it's a big thing, you could imagine shipping just a flat sheet. And if you order 10 things, you just get 10 sheets, each with pre-patterned to fold into your desired object instead of having to ship bulkier 3D objects, at least in some scenarios. In particular, folding sheets is a great way to go if you want a lightweight structure. Traditional 3D printing technology is great if you want to build a solid object, but not so great if you want to build a very thin, hollow form. Origami is sort of the natural way to do 3D printing in that setting. So here are some examples. Here's a simple one where the goal was to make a very cheap microscope. So this is a $1 to manufacture microscope. It works pretty well. It's drawn over here. And 140 times magnification, and all of the sort of technology or the interaction with this structure is based on just a bunch of cut sheets with some simple folds so that you can interact and move these parts left and right. So Origami was great because they wanted to be really cheap and have a simple manufacturing technique. Next example is a recent one from a PhD thesis by Sam Calisch here at MIT, where he made shoe soles out of cut polypropylene. So this is a combination of cutting and folding that you see in the animation on the top right. And the bottom right is him actually running with it. And what's impressive, and on the left is manufacturing tools that he designed for actually assembling the structure. What's really cool is that if you set the geometry right, you can get the folded polypropylene here to behave similar, in some ways even better than high-end foams that are used in traditional footwear. And so while each of these foams took years of development, he was able to tweak the parameters. This is a stress strain the function of the material. He could basically change the material properties just by changing the angles in the folding and get really good performance compared to these foams and just with little tweaks. And he says they're nice to run in. So, you could imagine this is still in the research stage, but you could imagine this in future shoes. Here's another example of using folding actually for traditional 3D printing. Nervous Systems, which is an artist group here in Cambridge, wanted to make a 3D printed dress just because it's cool. And the dress design they came up with is larger than most 3D printers. And so you couldn't just send this to the printer and have it made. But they had a digital model. And so they folded that digital model into a much more compact form in simulation. And then 3D printed that because they wanted the dress to be articulatable. They could make this sort of clump with a more normal size 3D printer and then unfold it and deploy it and wear it. And speaking of deployable, an exciting aspect of origami is that you can make a transformable structure that actually changes its shape dynamically. And so you can take, for example, a tube and fold it down to a small size. One application for that is to make a stent, which goes inside your body, say for non-intrusive heart surgery. You want to take a very small folded form of the stent, push it through small blood vessels till it gets to your arteries near the heart, and then expands and declogs the arteries. And on the right, we have a prototype of a telescope lens. This is a 5-meter version. The goal is to make a 100-meter version to send into space. In space, there's lots of room for a giant telescope lens, but you have to get it there with a space shuttle. And space shuttle has limited size, so you want to fold it down to a small size, fit in the space shuttle, send it out, and then it deploys and opens, and you have your giant lens. Another more recent deployable example is an origami shield. So this is a bulletproof shield. It's made with 6 layers of Kevlar. But Kevlar is quite flexible, and so you can design it to fold. So this has some rigid panels glued on top of a sheet, 6 layers of Kevlar. And so you can have a very compact structure. It's easier to carry around. I think it's still a little bit heavy, but you can put it in your car or whatever. And if you need it, hopefully you don't, you can deploy and hide behind it. It's been tested. And it's surprisingly robust. And so you have this interesting interplay between flexibility and rigidity. And in the spirit of energy absorption, back to Sam Calisch's PhD thesis, he's been experimenting with building better bumpers in cars, better crumpling. So if you can design a structure that crumples a lot, where it takes in lots and lots of creases, that's basically absorbing energy. The more energy you can absorb, the less the impact is when you crash your car. And so he's been finding ways to, out of not super strong material, be able to make highly energy absorbent structures just by folding. And so you might imagine this in future safer cars. One direction we've been exploring a lot is using folding to make robots. This is a lot of fun. You can imagine in school, for example, every kid can make their own custom robot for about $10 or $20 of material. Ideally, you have a laser cutter, or you could cut it by hand with scissors. Here we're laser cutting a sheet of plastic with little tabs, and you fold it together and you get a robot. This is not a working robot, but here are some examples of working robots where you also add in a couple of motors and some electronics, and they can run around, grab light objects. These are, of course, making very lightweight robots, so they're not as stiff as maybe traditional robots, but they can still do lots of fun things. And you can make a different robot every day and have fun with it. Yeah, and here's a somewhat smaller version. This one actually self-folds. That's a hot plate that folds the robot into, and now it's magnetically controlled. So it's walking around. Not shown are a couple of big magnets that are pushing it around. You can remote steer it. It can swim. It can push around even lighter objects, but you have pretty fine control. Even when you have other metallic objects in the environment, you can move this robot around. And so if you need some tiny robots that do to remote steer, you can do cool things, and it doesn't hurt humans. And if you use the right material, it will biodegrade afterwards. So in the future, we imagine an ingestible robot. So here, where you eat this thing and it navigates your body. The doctor can remote steer it, bring it to, say, where cancer is, and then have it eat away or explode or near the cancer. So with a very small robot, you can imagine doing internal surgery in a much safer way than currently possible. One of the challenges, so I just showed a whole bunch of different applications of origami. So I'm going to come back to mathematics and how we can model all these things. One of the challenges with making real world folded structures is that material, especially other than paper, is quite thick, and you really need to deal with paper thickness. And one of the first people to analyze this was a high school student, Brittany Galivan, 2001. And she studied this classic problem: if I take a piece of paper and fold it in half and fold it in half and fold it in half, how many times can I do it? And the answer really depends how thick your material is. If it's zero thickness, as us mathematicians like to work with, then you can do it as many times as you want. It's very hard to buy zero thickness paper at the store. So in general, it depends how thin your material is versus how long it is. If it's long enough, you can compensate. And the big thing that happens is when you take, say, a folded sheet like this and you bend it in half, of course, the number of layers doubles. That's not by itself bad. The problem is, to execute this turn, you use up a lot of length of material in this curved part of the folding. And this part will never fold again. You can only fold through the straight part. And so you actually end up consuming length. And so what matters is the ratio between the length and the thickness of the paper. She computed that if you want to fold a typical piece of paper in half 12 times, you need about half a mile. And she gave herself a little slack. So she used 3/4 mile piece of paper, which is roughly the longest piece of paper you can buy. It's a jumbo roll of toilet paper. And folded it in half 12 times. And this is the Guinness World Record of number of folds for real paper, and probably will remain so until you can buy a 3-mile long piece of paper. And so we try to incorporate this thickness model that she came up with into more complicated designs as well. So this is a simple crease pattern that works when you're folding a 0 thickness sheet of material. But now, if we tweak that crease pattern, double each of the creases, cut little holes at the vertices, then we can actually fold it with thick material. Prove that. And so this is a nice general construction where you can design with 0 thickness and then turn that into a folding structure that works with thick material. Here's an example of folding some really thick foam core just to exaggerate what's possible. And yeah, it folds into, this is a model called the bird base in origami. And there are a bunch of other techniques for this kind of thick folding design. Which leads us into origami software. I've mentioned a couple pieces of software, like this is Origamizer here. This is Tree Maker, first one I mentioned. There's a growing wealth of origami software tools. They're all generally free and open source, so you can go download them, play with them. And I want to show you a couple more that you might enjoy playing with. So the first one is one of the most powerful tools, especially for origami research, is called Freeform Origami. It's by Tomohiro Tachi, who I've mentioned. And it simulates rigid origami. So this is if you have rigid panels connected by hinges, there's not a lot of techniques. This was a tool that really helps you check whether your model really folds. But then what's happening in this top example is even cooler. So we started with a pattern, and then Tomohiro's dragging with his cursor, pulling on different points and reshaping the 3D surface. And then the software is solving for what crease pattern will fold into that. So you can start with something relatively simple, and then, so here's the starting point. This is called the mirror ori, very, very classic pattern used a lot, rigidly folds. And as he drags on those points, he can, the software finds what crease pattern will fold into that structure. And if you make gradual changes, you can find reasonable crease patterns. And so now you can really sculpt the paper into the 3D form you want. That's really cool, powerful. On the bottom, you see another fun thing you can do with the software, which is, he calls it Origamize. This is an old notion of Origamize. And it turns that surface into this tessellation pattern in 3D. It's not exactly the surface you asked for, but it's relatively simple. And here's an example of one of those structures actually folded out of spring steel. So yet another tool. A tool that I've worked on with Amanda Ghassaei, she was a student here at MIT, is called Origami Simulator. This is a fun, a simpler version of something like freeform origami. It also simulates how to folding of paper. And it does so a little bit more loosely. It's not necessarily physically accurate. It's as if your paper was a little bit stretchy, which is not good if you are designing rigid origami like a deployable origami shield or something. But it's quite flexible and robust, and it works with a lot of origami models. And it runs in your web browser, so it's very portable and relatively easy to use. So here it is. We have a surface here, which is folded. It came from this crease pattern, and I just drag the slider at the bottom, and we fold it into this network tessellation of squares around. Let's do some more examples. I'll go back to flat. So we can take, I don't know, dragon, fold it into dragon. These are just some patterns that we pre-programmed in here, but you can draw any pattern you want in a vector drawing program like Inkscape, and then upload it here, and you get, let's see, what would be another fun one? Maybe honeycomb. This is actually similar to the, I think the folded shoe soles that I showed you earlier. Uses a mixture of folds and cuts. And I want to go back here. Let's do a pop-up book for fun. How about a castle? So this is something easy you can make at home. A single fold pop-up book. If you make it out of stiff material, then everything will fold together. And another more complicated example. So this is a crease pattern designed with an algorithm, which I'll show you in a little bit, that folds into the words hello world. And so you can see it's pretty fun and flexible and great way to, we use it a lot to just test out, did I actually write down this crease pattern correctly? Does it fold? And it will check. And it's open source, so you can modify it however you want. Here's some more examples. This one takes a little bit longer to run. This is a design that we proved actually doesn't fold. So if you take a regular n-gon, it's often done with a square, and you fold concentric copies of itself, alternating mountain and valley, and you fold the diagonals. In real life, you get a 3D structure that looks like this. But what's drawn here is the stress. This is how much or the strain, how much you've stretched the material. And you can see there's a lot of red coloring still in that pattern. Usually when you fold a pattern, it ends up completely blue because it's happy to be in that folded state. But with perfect unstretchable material, in fact, it's impossible to fold anything out of this crease pattern. We proved that. And so here the software is just kind of verifying, yeah, you get something, but it's stretched, it's stressed out. Here's another cut pattern. This is beautiful, designed by Miyamoto. And as you've seen in a lot of the practical cases, we care about cuts in addition to folds, and so we support that too. You can even play with this software in virtual reality. If you have, say, an HTC Vive, you can grab on this piece of paper. And so in the future, you can imagine you don't even need real material to fold, at least to play with research about folding. You could do it in a completely virtual environment, though this is still in early stages. Okay, so with all this different software, we'd like it to all work together. And so we're also been developing a file format for communicating crease patterns and folded designs that's tailored to origami, where you can have multiple layers stacked on top of each other. You need additional structure to specify. And so there's, so basically all the tools that I've shown you speak this fold format. And so you can save the output of Origami Simulator and load it into Tachi's Freeform origami and play with it, and then save it and reload it in the other software and go back and forth. And that's helped research a lot. So another piece of software and algorithm I want to show you is a relatively simple style of design, but kind of cool. We call it maze folding. And so here's a crease pattern in the top left that folds into this 3D structure, folds a maze. If we go back to web browser here, here is maze folder in action. So you can say generate a random maze, and this is the thing you want to fold. And this is the crease pattern that will fold it. And you can change your maze around to be whatever you want, and you get the crease pattern. And the way, and the theorem here is that you can take a rectangle of paper, say m by n, and fold it into an m by n sort of extruded maze out of a surface with a constant scale factor. The constant depends on this height, but say if you call this height 1, then if you take a rectangle that's 3 times larger than your maze, you can fold it into the maze no matter how complicated the maze is, which is really cool. And so this is a nice example where a constant fraction of the material gets used in the design and the final folding, and we can prove that that always happens. The way you prove that this is always possible is relatively simple. We designed little structures, we call them gadgets, that fold into a particular type of corner of the maze. This is a degree 1 vertex for the mathematicians, where you have one wall coming at a single edge, also like this edge and like this edge. So all of the pink examples on the left are the same crease pattern, just rotated. Or for example, this pattern folds into this 4-way merge of 4 walls. And you just design these individual foldings. These are designed by hand, by Jason Koo, actually, so that you can join them together and get one big crease pattern that folds into any maze you want. And you can, recently we generalized this to triangular grids and hexagonal grids, and you can get similar kinds of results, though the foldings are complicated. And for fun, my dad and I also really like designing fonts. And so we came up with this font for maze folding. So on the right is a crease pattern, not drawn to scale. It would be like 3 times larger. Or I guess about 2 times larger, depending how you measure factors. area versus length. Let's see, then it folds into the pattern on the left. So we're folding the entire alphabet out of one giant sheet of paper. This has not been done physically, could be though. I have a very big piece of paper. And what I've highlighted on the right, these little gray patches are what end up being the vertical walls over here. The ones that I just highlighted are those two groups. And it gives you some idea. And if you stare at the right diagram enough, you will eventually see the letters, but it requires some rotation in your head. But it's kind of fun. You can kind of make a puzzle. So I can write, for example, my favorite text in a SIAM, for example. So here's what you would get by folding if you folded this crease pattern. So as is, this is like a secret message. We call it a puzzle font. So this folds into a unique structure, but it's, unless you're well trained, you can't really see what the letters are here. And you could sit there and fold it, or just think about it for a while, look for where these flat panels are and where they must be in 3D, and eventually figure out, oh, it says SIAM. So this could be your next logo. And my dad and I have designed a bunch of fonts all based around different mathematical theorems or open problems. A lot of them have puzzles embedded in them, and I'll show you a few more during this talk. I used this particular font for, or I guess different form of it, for advertising a class that I teach at MIT. At MIT, everything is a number. So 6 means ECS, and 849 here means geometric folding algorithms. So this is the class corresponding to what I'm talking about here. And in general, the vision of computational origami design is you start with what you want to make. You use an algorithm to figure out how to make it. And then, at least for now, humans fold those crease patterns into the 3D form, and then that matches what you wanted. And if you're interested in seeing the details of how these kinds of algorithms work, you can watch videos of me lecturing about this stuff for, I think, about 30, 40 hours, but you can watch whichever parts are interesting to you, all free online. And we've also used this font to design artwork. So this is a design with artist Sarah Stengel, where on the top we have a crease pattern. It has these little gray regions that don't look like too much by themselves. And if you fold that crease pattern, you get the 3D structure of the word yes here. So that's what the creases do. But at the same time, the gray patches come together to form a false shadow hiding behind yes, which says no. So yes or no, what does it mean? Conflict, that's the message of that piece. This one has actually been folded. It took, I think, a couple of days to fold. Here's one that I hope will never be folded. It's incredibly complicated folding pattern that makes 3D structure of science, because science is hard, and then hiding in the background is art. I think science is art, vice versa. All this folding by hand, though, is really tedious. So can we get sheets that fold themselves, or robots that fold themselves into desired folded forms? So in the bottom, you see a couple of examples of relatively simple foldings, just making origami style patterns like this crane or this boat. This particular sheet on the bottom left folds into a boat or a paper airplane design. So it can make multiple patterns out of the same sheet. In the top right, we see a self-folding robot. So this is with the goal of making a walking robot. So we've just started with a laminated bunch of sheets, laser cut, and put on a couple of motors and batteries. And after 4.5 minutes, it folds itself. So here's what the original structure looked like. And as soon as you plug in those batteries, it starts self-folding, pushing along all of those creases to make it fold into a fully working robot. And then, as you saw, it walks off. So we're still in infancy here, but because these are all relatively simple designs, but the idea is you could make super complicated folding designs all with a sheet that, as soon as you sort of plug it in, folds itself. So one idea here that you saw, especially in the bottom left example, is one crease pattern that can fold into any design you want. We call this a universal hinge pattern. A hinge can be folded or not folded. And one early result in this area is if you take an n by n sheet of this pattern, which in origami is called box pleating, square grid plus alternating diagonals, then you can fold any surface you want made out of roughly n different cubes. And so if you take a large enough sheet of this stuff, you can make anything you want. Here is a relatively simple example of a pretty complicated crease pattern, but it folds into these 4 cubes like a Tetris shape. And that same size sheet can fold into any pattern of 4 cubes, which is cool. And this is nice, it's universal. You could make one sheet that can fold into anything, but it's also a little unsatisfying because it wastes a lot of material. If you think about the surface area of an n by n sheet, that's about n squared, exactly n squared, if you have unit squares. But the surface area of order n cubes is order n surface area. So we're wasting a huge amount of material here. N versus n squared is a big difference. So for large n, this is not actually very efficient folding. So we've been exploring more efficient foldings, at least for certain designs. So one set of structures you might like to make is what's called an orthogonal terrain, like this car here. So think of it as a mountain range that has no undercuts. So monotone direction. See here, Z, sorry, we're in Canada. This method is provably efficient. We get a similar kind of constant scale factor like we did with maze folding. So as long as you have a mountain range that doesn't get too high at any place, you can build these structures quite efficiently. This is the crease pattern that folds into this pretty complicated car. That's a pretty recent result. The most general result we have that's really efficient is if you take a strip of material, this, and fold here with the square grid plus the same diagonals. It turns out that works a little better. Then you can fold into any surface with almost the same surface area. You just lose a factor of 2. So 50% of the material here will end up on the surface as long as you have a surface made out of cubes. I didn't mention, but if you have some other surface like a bunny, you can, of course, approximate that surface with lots of little cubes in the same way that we pixelize 2D images. You can voxelize 3D images into little cubes. And so then you just need one strip of material and you can fold into any surface. So this structure, if it was length a couple hundred, could fold into this dog and could fold into any other shape with the same number of cubes. And of course, we designed a font around that. So this is a way to fold strips, in this case of varying lengths, into each letter of the alphabet. This is the A, this is the B, this is the C. And there's a online app you can play with this. So you can write, for example, SIAM again here. And this big strip of material and crease pattern will fold into SIAM here. So maybe it's a block, and it will fold back and forth into a set of letters you want. Cool. Now this reminds me of a lot of more practical directions of how to take a strip of material, in this case, a long strand of DNA. This DNA comes from a rather harmless virus. It's really long, it's a few thousand base pairs, and you can force that DNA strand to fold into any pattern you want. This is a structure known as, or a technique called DNA origami, introduced 14 years ago. It's used a lot in synthetic biology to make arbitrary structures. This is one of the first examples where they made happy face, and of course they can mass produce thousands of happy faces all at once. You can use it now to make 3D structures. There's a whole technology built around this. It's a similar idea of taking a long strip of material and folding it into your desired 2D or 3D structure. And it also relates to a mathematical concept called hinged dissection, where you take a chain of blocks here, hinged together at these points, and fold it from one shape to another. This is a design that is over 100 years old, and it folds from a perfect square to an equilateral triangle. It's great if you have a table And sometimes you want to have 4 people seated at the table, and sometimes you want 3 people seated at the table. I know that's not terribly relevant these days, but maybe you occasionally have 1 person visit. And this way you can reconfigure your table accordingly. And for a long time, it was unsolved whether these hinge dissections existed for all shapes. We proved a while ago now that this is always possible. You can take any finite set of shapes of the same area, and there's one chain of blocks that will fold into each of them. And the most practical forms of this theorem are like what we were doing before. Here I'm showing you in 2D. We'll go to 3D in a moment. If you take a shape made out of lots of little squares, little pixels, there's one hinge dissection that folds into all of them. In fact, it's just you take these half squares, and if you have 2n of these, you can make any shape you want out of n squares. And similarly for hexagons and all other shapes. So if you have any shape made out of repeating copies of things, then there's a really simple way to hinge dissect them all and make one chain that can fold into all structures of a given size. And so here's an example of applying that to make a font. So each of these letters is made out of the same number of half squares shapes. These are called right isosceles triangles. And so here is the letter A, for example, expanded out. If you take this chain of 128 blocks here, you can fold it into any other letter of the alphabet or a square. This is actually the first mathematical font we with, 2003. You can generalize this to 3 dimensions. So you can take a bunch of cubes, hinge them together with this particular pattern, and prove that it will, if you take 8k cubes, you can make any shape you want out of k larger cubes. So you can go, for example, from this 3D cross, which is from a Dali painting, folds into a hypercube, or into this orthogonal donut, and any other shape made out of 8 cubes. And we applied this once with Laurie Palmer to make a sculpture. So this is a chain of about 1,000 blocks connected together by piano hinges that you can fold. It's an interactive sculpture. You pick up these gloves so you don't get splinters, and you can reconfigure it into any 3D structure, provably. But we can also use this to make robots. So we designed a robotic system with pivoting structures and a design tool so that you can, for example, make this dog again out of one strand of, now we're working with solid material instead of a strip of paper, and build robots that fold into any 3D structure you want, sort of like Transformers or T-1000 Terminator robot that can change its shape into anything it wants. So these are at different sizes. Here, each square or each cube is about 1 centimeter. Here, each cube is about 10 centimeters. And here, each cube is about 100 centimeters. And so depending on how big a structure you want to build and how fine a resolution you want in reconfigurability, the dream is, each gadget that we hold up could actually be made out of lots of little cubes, and you push a button and it can reconfigure from this pen I'm holding into bicycle that I can ride off. Subject to preserving density, you could imagine folding anything you want. Okay, so that was a tour through kind of folding long one-dimensional strands. Let's go back to some computational origami. And maybe I will switch to camera only just for dramatic effect. So here, let's take a piece of paper, which I've pre-creased here, but it's just a rectangle of paper. I fold it into a flat pattern, flat origami it's called here. And you can see there's a line drawn, and I'm going to take my scissors and fold and cut along the straight line. In this case, I get 2 pieces. Keep one of them and unfold the piece, and I get a butterfly. Okay, simple example. While I'm here, here's another pre-folded rectangle, which I will cut to the correct side. Hear that for the ASMRs. Okay, fold, cut, and out of one straight cut, we get swan. So pretty cool. And maybe I'll do one more example. So here is a very simple design where I take a rectangle of paper, I fold down the middle, I fold over the side, and then I fold a diagonal, and then I cut along this line, to this side. Never know ahead of time whether these are going to work. They should work in theory, but you know, in theory, there's no difference between theory and practice, but in practice, there always is. So play this one I haven't tried in a while. Unfold, we get letter M for math. Cool. Slides. So this is what we call the fold and cut problem. And it's motivated by magic. This problem goes back to 1721, the earliest reference we know, as a Japanese puzzle book. And on the left is the puzzle. Can you make this Japanese emblem shape by folding and cutting paper? Apologies, this is in ancient Japanese, so it might be hard for you to read. And on the right is the solution. You just fold a piece of paper as drawn, and you make single cut drawn here, and you get that pattern. It was July 4th weekend, so should talk about Betsy Ross making the American flag. And there's so this is what you're seeing here is a 1932 painting about an 1873 story about something that maybe happened in 1777. It probably didn't actually, this is probably a fictional story made up in 1873, but it's a cool story. The story goes that George Washington wanted to put six pointed stars on the American flag because it's easier to find equilateral triangles. And Betsy Ross says, oh, no, it's really easy. Here's a cool way to make 5 pointed stars. You just take a piece of paper, you do a few folds, and as you can see on the right here, she's folded and is about to cut and then pull open a regular 5-pointed star, which is a technique that Harry Houdini also discovered or at least published and probably performed in 1922. Before he was an escape artist, he was a general magician. And this is where we first heard about the problem, not that we were around in the 20s, but this is one of this first references that we found about folding and one cutting. This is the method for making a 5-pointed star. It's like a magic trick. You can impress all your 6-year-old friends by downloading one of the patterns I just showed you and folding and cutting. And we heard about that Houdini reference through Martin Gardner, who is the father of recreational mathematics and lots of fun and awesome things. Definitely recommend reading all of his books. And there's this one book, New Mathematical Diversions, that shows this article and references the Houdini thing. And he posed this as a problem. What shapes can you fold or make from folding in one straight cut? And this, for example, is the crease pattern that if you cut along the black line here, you get the swan that I showed. And in general, there's an algorithm that tells you how to do this. You give me any polygon or any set of polygons, any set of cuts that you want to do, straight line segments. There's a folding, and you can find it with an algorithm that brings all of those cuts to a single line and has nothing else along that line. And so then you can cut along the line and you get exactly the pattern you want. So in principle, I could make this, this turtle and this swan and this butterfly all at the same time with one cut from a big sheet of paper. So of course, there are practical challenges with actual paper thickness. This is one of my first papers in this area. Still a lot of fun. It has some applications to airbag folding where instead of bringing cuts to a common line, you want to bring surfaces like panels of your airbag down to a common plane so that it's all flat. So you can store a big airbag, 3D polyhedron surface inside a narrow structure like a steering wheel and fold it nicely so when it deploys, it doesn't hurt you. And of course, we also came up with a font. This is more recent, but like the letter M that I showed, for every letter that you want, there's a way to fold it, and it's the software does it. So I can write SIAM, for example, and you get, in this case, a sequence of folds and cuts. Here I've turned on puzzle font mode, so you don't get to see the letters. You could present this as a handout and like do this with your squares of paper. And when you cut along the red line, you will actually cut along these red lines, which gives you the different letters. So you end up with SIAM as your thing. Cool. So that was the fold and cut problem. The last topic I want to show you is curve folding. So here I've got to get some paper folding sound. Hopefully you can hear that. So this is my dad folding along concentric circular creases to make this cool 3D kind of Pringle shape. So the crease pattern's down on the bottom right there. And this is a design that actually goes back to the Bauhaus in the late 1920s by a guy named Joseph Albers, or his students first came up with this design. You cut a circular hole out of a piece of paper, crease concentric circles, and the paper just wants to fold into this really cool 3D form. And we just like to understand, how do curve creases work? They seem to make really rich 3D geometries with relatively simple crease patterns. So for starters, my dad and I started exploring this problem just from an artistic perspective. You know, let's explore, let's see what's possible. We started out just making models, and they're like, oh, these models look pretty cool. Let's turn them into sculpture. And so we used nicer materials. These are some of the first pieces we made, which are at Museum of Modern Art in New York. Trying to take these circles to a new level. Each of these is folded from similar crease pattern, just from a circle that goes around twice, 720 degrees instead of 360. These designs are at the Renwick in DC, and they're based on the original circle design, but combining multiples of them together. So this is 2 circles combined, this is 3 circles combined, and this is, I think, 5 circles combined. Also, we're using paper that's light colored on one side and dark colored on the other with these models. And so it's really exciting to see, here's what it looks like putting one of these pieces together. Of course, in real life, it can take days to find a nice assembly of pieces, but in movie time, it only takes a few seconds. But each of these pieces of paper wants to go into some natural equilibrium form found by physics, but when they interact with each other, you can kind of control that form and get it to fold into some really cool shapes. Here are some larger pieces. And this is maybe the largest structure we made just temporarily for a fun photo shoot. That's my dad and what his office looks like. And so before I get to the math side, let me show you a few more fun artwork. So we have gotten to printing onto the sheet of material some pattern that we fold. So the first pattern we folded is this short story called The Destructors by Graham Greene, which is the basis for Donnie Darko, if you've seen Donnie Darko. In both the movie and this book, which they're reading in the movie, the idea is that destruction is a form of creation. So we took this short story, and this seemed like permission to destroy it and fold it into a 3D sculpture. And if you look closely, all the text is still in there. You could still read it. You just have to destroy the sculpture to read the text. Here we've printed a QR code on the paper before folding it. And cool thing about QR codes is they're an error correcting code, so you can cut a relatively large hole out of the center, and you will still be able to scan this with your phone. If you hold your phone up to the screen quickly, it might scan. It takes a little while, but it then says folding error to predict what's going to happen. Of course, once you fold it, you can no longer scan it. Here's a nice pattern based on a model of a sunflower and a Warner diagram, if you know those things. So just exploring different cool mathematical patterns we can print, or in this case, linguistic patterns. This is all of the words that Shakespeare ever used that contain the word red inside of them. So sphered and pestered and aired, but also more interesting ones like credo has red in the middle. And makes for a very cool pattern. And yeah, nice Shakespeare reference. This is an imagined collaboration with Joseph Albers, who maybe came up with this concentric circular folding model, but he also did a lot of really interesting artwork, like this design, which is meant to look like the Manhattan skyline, but it's just sort of very bold, solid color. So we reimagined that design into a circular pattern and then folded it up into collaboration. We also fold concentric circles out of glass, although this is much harder. And because my dad and I are both glass blowers, he taught me to blow glass, and we try to combine paper and glass in different ways. So these are some examples of inserting paper into the center of a glass vessel. And you can get some this constrains the paper to fold in a particular way, and it gets us even more power in expression. Okay, so all of this exploration in the art side led us to understand better and better how curved crease origami works from a mathematical side. So we have a few papers, in particular these two, that characterize locally what happens at a curved crease. That's sort of well understood, but now we even understand how the connections between two creases work out. So all of these straight lines, which are called rule lines that connect between creases, they have a constraint between any two creases, and those two local relationships characterize what's possible with curved crease folding. We still don't have great design algorithms here, but we kind of understand, we can analyze models to see how they're working. And so we've applied this in particular to one of the first people to fold along curved creases, David Huffman, famous for Huffman codes used in every sound file you've ever listened to, for example, or every zip file. But he also did a lot of curved crease folding, especially later in his life. He died back in '99. I met him right around then. But he left behind hundreds of designs and sketches and lots of notes about different crease patterns, which are now at the MIT Museum, available for looking at. And he designed with this particular style of how rule lines behave. I won't go into details, but it involved conics, which are hyperbolas, parabolas, and ellipses, and they behave in cool ways. And we characterized when this works. Can you combine an ellipse with an ellipse? Yes, provided the foci of the ellipse, the focus points, are the same. Or you can combine an ellipse with a hyperbola, provided their eccentricities are reciprocals of each other. So we sort of figure out when this works, but you can never, for example, combine a circle with a parabola. And so you can look at his design and say, okay, cool. This is his hand-drawn version and our redrawing of it. And this is his folded version. And this is our reconstruction on a computer to show, yeah, this is really working. Because he designed these focus points and these parabolas are scaled versions of each other, that guarantees that this rule pattern will work. Or you can look at other models like his tower here and discover that it cannot work with the same kind of rule pattern if the rule lines are supposed to reflect, which is a technical constraint, but seems like a natural one, because here he's working with circles and parabolas, and if you look in the table, that's not allowed. But of course he folded this, so what's happening is probably a different rule pattern like the one that we've drawn here, which was found computationally. So the conjecture is this crease pattern does work. Here we're looking at a coarsened version, it's not smooth, but the conjecture is even the smooth one works provided you change the rule lines in a different way. So still lots of work in progress here. I'll just close with a fun font that we just worked out for. These are crease curves that you could draw on a piece of paper, and they fold into letters of the alphabet. So this folds into the A, this folds into the B. Pretty good puzzles. You have to imagine locally increasing the curvature all along the arc, and on the top is an example of even a few concentric pleats like that folding into a capital letter B. So at least we're starting to get to the place where we could compose different designs together and fold a complicated pattern. If you want to learn more, about geometric folding algorithms, there's the book that was mentioned at the very beginning with Joe O'Rourke. There's the online classes that I mentioned in the middle. We're going to have a new online version of the class at MIT in fall 2020. You can watch then, but in particular, we'll be watching the videos that were pre-recorded in 2010 and 2012. You can already start streaming those if you like. There are a couple of movies about the art and science of origami. The first one is called Between the Folds by Vanessa Gould in 2008. Still a great film. It captures a lot of the community. And there's a more recent Nova documentary called The Origami Revolution. It has some of the more recent examples, like Tomohiro Tachi is there, and you can see us Skyping together because he lives in Japan and I live in Boston. So we do a lot of meetings online. And that was our tour of Mathematics Meets Origami. Hope you enjoyed it and happy to take questions.